Okay, welcome back to Organic Chemistry 2342. We're going to continue on with chapter 17. We're going to finish up with anhydrides and other derivatives there. And then we'll have a little bit of time for review. What's great about this set of chapters, these two chapters here, is it's all about the different chemistries associated with the carbonyl compound. And so when we have that aldehydes and ketones, we have very bad leaving groups, and so we tend to get addition reactions on it. Once we go to the carboxylic acid derivatives, we start seeing that the leaving groups become much less basic, and therefore they're much better leaving groups. And we actually start to see many, many more reactions that end up being substitution reactions and not addition reactions. And so that's the driving theme in these two chapters here. And so the compare and contrast between the good leaving group, bad leaving group should lead you to understand a little bit better the idea that substitution happens with good leaving groups, addition happens with bad leaving groups. Okay, so that being said, let me go ahead and share my screen. Share screen. There we go. Let's see if it likes me today. Yay. All right. So there we go. I'm going to move my viewing screen way over here. And there we go. Okay. As again, this will be posted online after this, in between this and our group activity, so that you can review this as is. Remember that homework is due at midnight tonight. As soon as it is due, we can go ahead and start reviewing that and figuring out what you did and didn't do, and study those things in particular before the exam on Friday at noon. Okay, again, it should be a little less stressful this week. I changed a couple of the parameters, so it should be easier for people with lower bandwidth to get into and stay in the exam without being kicked out so many times. So hopefully we'll have a much smoother week than we had last week. But let's go ahead and continue on with part 4 of our chapter 17, which is the carboxylic acids and their derivatives. And particularly, we've moved on from acid chlorides down to acid anhydrides, okay? So the acid chloride was the most reactive of the set because it had the best leaving group. The chloride ion was the the weakest base of the set. And so now we're moving on to the second one, which is the anhydride. The anhydride is basically just a carboxylic acid that has water removed. Unfortunately, unless you're forming a ring, you cannot just heat up 2 carboxylic acids and expect it to dehydrate. This only works if you can make a 5 or 6 membered ring. Okay, so if we look at the bottom half here, this 5 or 6 membered ring available to us means we can do it. Notice these are very high heats, okay? In straight chains where you don't have the entropy to close this ring, the most likely thing to happen is just thermal decomposition and extrusion of CO2. So this cyclization with heat only happens with these small rings, the 5 and 6 membered rings. So that means the most practical way for us to make it is to actually use the more reactive species, which is the acid chloride, okay? And we have 2 ways of doing that. The first way is we take a carboxylic acid and a carboxylic acid chloride, and then we add a base to it, a mild non-nucleophilic base. And in this case, we're using pyridine. Pyridine was introduced to us in the aromatics chamber, in the aromatics benzene chapter as a basic material that we can use it to deprotonate things. So in the case of this, we have their acid chloride right here. Technically, our oxygen on our carboxylic acid comes in and acts as our nucleophile, kicks out our chloride ion, and then it loses hydrogen to give us our salt of our base, and our acid we generated, which was the HCl, and we generate our anhydride. If you don't want to do that, what you can do is pre-make your nucleophile by deprotonating ahead of time with a base. Remember, we can use very weak bases. We would just need to use a base that is in a non-aqueous solvent, because if we had water in our solvent, it would react with the acid chloride immediately. So if we can make our carboxylic acid salt in an anhydrous conditions, we can add our acid chloride and generate our anhydride as well, and then some kind of salt on the side. Okay. So the key here is that we had to use something much more reactive to generate this next level of reactivity material. So in both cases, we're using this acid chloride for our main synthesis of an anhydride. Okay. Once we form that anhydride, it does a lot of the same reactions that the acid chloride does, except that it cannot make other anhydrides. Okay, so they easily react with water to go to the carboxylic acid, which is what we'd expect an anhydride to do because it would just hydrate and form the carboxylic acids. The next thing it can do is react with alcohols. And in the process of the alcohol, the lone pair on the alcohol acts as our nucleophile and displaces the carboxylic acid and then reprotonates it to give us one equivalent of carboxylic acid and one equivalent of ester. Note, we typically use symmetrical anhydrides because there is no selectivity on whether or not this goes there. So if you have an ethyl chain and a methyl chain on this anhydride, you'll get a mixture of the products and it'll be very, very messy. So you have to keep in mind we typically use a symmetrical anhydride when we do these reactions. Okay. So then, just like with the acid chloride, when we have amines and, excuse me, it's water, trust me. Anyway, okay. When we have amines, we have the same problem that we had with the acid chlorides in the fact that the amine also acts as a base. It's a nucleophile because of the lone pair on it, and it attacks our carbonyl compound. However, when it, the leaving group is the acetate ion or the carboxylate ion, and that is going to be counterbalanced by the amine. And so we always have to use excess of our amine, just like with the acid chloride. One half of it's going to generate our salt, which is our byproduct, and the other half of it is going to generate our amide. Okay. And again, this can be a primary, a secondary, or a tertiary amide, depending on which amine you choose right here. So if you choose ammonia, you would end up with your primary. If you used dimethylamine, you'd end up with your tertiary. Okay. And of course, our last reaction available to us, it really doesn't get us very far. It just gets us back to our carboxylic acids. In the use of just water, we'll end up with two equivalents of carboxylic acids because we have two protons to allow us to do that. In the case of base, we will end up with two carboxylate anions because it is deprotonated by the base as soon as it hydrolyzes. Okay. So we've made acid chlorides and shown their reactivity. We've made anhydrides and showed their activity. Well, there's also a very interesting thing that happens with these carboxylic acids, the ability for it to rearrange and eliminate CO2 from the system. Because if you think about that carboxylate ion, it's already got a carbon with two oxygens on it. All you have to do is rearrange some electrons and you can liberate CO2. Okay, and when we do that, this is called the decarbonylation reaction. Okay, so we're removing that carbonyl compound and it's called a decarbonylation reaction. Now, if you just took a carboxylic acid and heated it up, it would spontaneously decarbonylate. And so the decarboxylation would remove that carboxylic acid and generate an alkane on it. Okay, this typically takes a lot of heat to do this. Like when we tried to make an anhydride by just heating, if you didn't form a ring, it would actually do the decarboxylation reaction instead. Okay. However, you can help that decarboxylation reaction by having some other oxygen species, specifically a ketone, 2 carbons over from your carboxylic acid. Okay, and in this case, we have what we call a beta keto acid, meaning we have a ketone that is 2 carbons over. So the first carbon over here, this is called the alpha position, and then this is the beta position right here, because it's the 1 carbon over and the 2nd carbon over. And if you have a carbonyl compound in that beta position, what happens is you can form this six-membered intermediate right here. And all we have to do is, once it rearranges into this six-membered intermediate, we just flip electrons back and forth, and you end up liberating CO2 and generating this structure here, okay? And that's called an enol. And we're gonna talk a lot more about that in a couple chapters after we've done carboxylic acid derivatives. And we're gonna look at these reactions we can do by forming and trying to make an enol or an anion associated with that. Okay, now one thing that we'll learn about these enols is that they are not as thermodynamically stable as the ketone. And so the proton transfers over here, the electrons kick up here, the electrons kick down here, these electrons kick out here, and the hydrogen transfers to give us our ketone here. So if we can form this six-membered ring with our carboxylic acid and a carbonyl that is in that beta position, this takes place at much lower heats. You can actually do it less than 100 degrees C, and you can remove that carboxylic acid group. It leaves the ketone, but it can remove that carboxylic acid group. And we'll show a lot more of those reactions later. Okay. So the last thing we want to talk about is derivatives of carbonic acid. Now, we said that the simplest of the carboxylic acids was the one with just the single carbon on it. It's also called methanoic acid because it only has the one carbon on it. Okay, and we also said that we typically don't use that in our organic chemistry a lot because it's very unstable. When it gets protonated by water, it rapidly decomposes to CO2 and water. So you will have, the best way to see it is to have it dissolved up in your fizzy drinks. That's actually carbonic acid when it's in the pressurized form. As soon as you release the pressure, any CO2 on the top starts being liberated from the system, and those are the bubbles you get from your bubbled water. Okay, so the fact that it's not very stable unless it's under pressure and that it rapidly decomposes means, well, we can still use it and we can generate derivatives of this carbonic acid just like we have the acid halides and the amides. So one of the derivatives of this carbonic acid is the diacid chloride. So instead of having two OHs there, we've replaced them with chlorines. And this right here is called phosgene. It's a gas, and it was originally used to make polyurethane foams and all these other things like that. It was also used in World War I as a mustard gas, which is why you can't keep it around very much. It's very hard to use, but it is a very nice chemical to use industrially because it's a gas, it's very small, and it's very reactive. Okay. In the case of once you can safely operate this in a chemical plant, you can do a bunch of different things with it. One thing you can do is react it with ammonia, and ammonia can be used to make urea. Urea is a really common reagent used in fertilizers and intermediates in other chemical processes. So, and it's very small and very easy to make and very inexpensive. So let me move this up. The other thing you can do with this is you can actually react it with two equivalents of an alcohol. When you do that, you create a slightly different functional group. Notice it looks like an ester, but instead of having a carbon bond on one side here, we actually have another oxygen bond. And so this is a compound, it's known as a carbonate. And you may have heard of polycarbonate. It's a type of Lexan, it's a clear plastic. It actually has this functional group and was traditionally made with phosgene. It's now made by another route here, but it's very similar to esters, but it has, again, another oxygen bond to it. And then the last thing we can do with it is to react with one equivalent of an alcohol and one equivalent of amine, and we'll end up with a new functional group called a carbamate, but industrially we call this a urethane. So your polyurethanes and your polyurethane foams all have this actual functional group in there, and it's noted by having the carbonyl and it's bonded to an oxygen on one side and a nitrogen on the other. Okay, so we go from a urea or a polyurea to a carbonate or a polycarbonate and a carbamate or a polyurea from that system. All right, so those are the major derivatives so far with acid chlorides, acid anhydrides, and then a little bit about the different derivatives thereof. The simplest of our carboxylic acid, dicarboxylic acids, carbonic acid. Questions on that before I move on to part 5? Okay, I will start moving to part 5. We have 2 things left to do before we end up breaking for today, and hopefully we'll have a little bit to talk about as far as review goes. But our next thing we want to talk about, we started with this idea of nucleophilic acyl substitution, right? Because we have better leaving groups, we can do a substitution reaction instead of just the addition reaction. It all has to do with that basicity. So moving on with the different functional groups we have, we started with the acid chlorides and we moved to the acid anhydrides. And now we're going to move on to the esters and amides right here. So if the acid chloride is most reactive and the anhydride is next most reactive, really the ester and the carboxylic acid itself are about equal in reactivity. And if we think about that, if you think about methanol or an alcohol plus water, they each have about the same basicity and they have the same acidity, which means they are approximately the same strength of leaving group. So when we look at esters and carboxylic acids, we tend to put them right in the middle of reactivity, and we can use them in a bunch of different ways. Sorry. Okay, so let's talk about how we would make the ester that we can use for these other functionalities. So turns out, because it's so similar to the basicity of water, what we want to do in this case is we want to use either an acid or base mediated system. If we use acid in the system and an alcohol, we're going to use that acid catalyst to the system, and we're going to use excess alcohol to drive the reaction to the ester, okay? So notice that when we're looking at these esterifications, the Fischer esterification in particular, it's an acid catalyzed reaction with a carboxylic acid and an alcohol here. The more alcohol you add, the less water you have in the end here, and you're driving the equilibrium to this way, okay? It is an equilibrium. If you start adding water to this side of the reaction, you can hydrolyze your ester to the other direction, okay? So that's showing you that their basicities and acidities are right about the same, and you can have to play with the equilibrium because it'll go back and forth, okay? So most of the time, to drive this reaction forward, you want to use something where it removes water from your system, either boiling off the water or having it somehow remove itself from there, or use a large excess of the alcohol so that it doesn't have much of a chance for the reverse reaction. Okay, so let's look at the mechanism of that. And in most cases, we use either sulfuric acid or HCl. In the organic lab that we actually use the sulfuric acid as that. We put the acid, the alcohol, and a couple drops of sulfuric acid, and that's all it takes to drive the reaction. Just a little mild heating at 50 degrees, and boom, you have a significant yield of your carboxylic acid ester. Okay, so as with most acid-mediated or acid-catalyzed systems, the first thing we're going to do is we're going to protonate some species. And in this case, we have the lone pair on the oxygen, making it is the easiest thing for us to protonate. Once we protonate that oxygen, oops, I'm going to draw my line here. Let's go to blue ink here. Once we've protonated the carbonyl oxygen here, that's going to make this part right here have a slightly positive charge, which makes this carbon more electropositive, okay? Because those electrons are going to be pulled up to the positive charge on the oxygen, making it more reactive to even weak nucleophiles. Remember, water and alcohol are weak nucleophiles because they're neutrally charged. Okay. Once we have attack by that weak nucleophile, we get this tetrahedral intermediate here. And so now we have a couple different things that can happen. We can either lose a proton off one of these oxygens, or it'll end up going back to the carbonyl type compound. So that's why each of these steps is in equilibrium here. If we are to lose the proton off of the alcohol portion first, that makes it the worst leaving group of the set. The other two alcohols become better leaving groups. And so if we were to transfer this proton to either of the other OHs, we would have a protonated species here. Okay, so now we have a protonated OH, which makes it, when it leaves, it'll leave as neutral water. Okay, so in the case of this reaction mechanism here, we have the lone pair from the oxygen coming in, regenerating our carbon-oxygen double bond and kicking out neutral water. Now our neutral water gets to come in and act as a base, and our neutral water can deprotonate the proton that it added in the first step, and we end up with our neutral species leaving, and we've regenerated our acid catalyst. Okay, so again, every step is in equilibrium, so the more alcohol you have in there, the more it drives it to completion. Okay, so if we want to hydrolyze the ester, if we want to force it back to the carboxylic acid, we have two options for us, right? We can either do it with acid or with base, because all we have to do is add water in that acid situation we just looked at. In the case of base-mediated hydrolysis, we actually have to have equivalence of base added, because we're going to end up creating the carboxylate ion. So we typically say it's acid catalyzed hydrolysis, but base mediated hydrolysis, because you need an entire equivalent of the base to drive it to the carboxylic acid salt and the alcohol. Okay. So now let's say, you're in that case, we're using a base. We're using a base to come in and act as the nucleophile to cleave off that ester, to cleave off that alcohol here. Well, the other reaction we can do is using amines as bases. It will also displace that alcohol. And in the case of any ester right here, all you need is any base. It can be ammonia, primary or secondary. Okay, it can't be a tertiary, because it will not reform the carbonyl, because there's no proton to leave. So we use a ammonia to make a primary amine to make a secondary, and a secondary amine to make a tertiary amide. Okay, and so these will displace all of these and generate your neutral alcohol species with that remaining proton from the amino compound. Okay, so again, carboxylic acids and carboxylic acid esters are about the same reactivity, and they can be switched back and forth using acid and base, or they can be turned into the even more stable carbonyl compound, the amide, by attack by the nucleophilic amine. Okay, so let's say you have an ester, but it's not the ester you want, okay? So, and you don't want to have to go back and hydrolyze it all the way down to the carboxylic acid. So there's actually another reaction we have that's called transesterification. Okay, just like in that equilibrium step between the water and the alcohol in the esterification right there, we can have that neither one of those alcohols will necessarily be more prone than the other to be a leaving group. So we can do what we call a transesterification, and this is typically done with an acid catalyst. And the way we do it is we take a lot of one of the alcohols, or take a higher boiling alcohol and mix it with our ester that we're starting with, and then it'll start exchanging. Okay, and so if you have an alcohol that boils at 100 degrees, and if you have an alcohol that boils at 50 degrees, and you're running the reaction at 100 degrees, slowly the lower boiling alcohol will boil out of your reaction mixture, driving the reaction toward this side of the equilibrium because you're losing this and it can't go in the back direction. So this is really, really commonly done in industry because you end up being able to regain this material to use in some other process, and you get your higher boiling or the desired carboxylic acid ester with just a drop of acid in it somewhere. Okay, so one of those common ones that are used is like this right here, where we can use methyl methacrylate. Methyl acrylate is commonly used in adhesives bonding. And to change the property of the adhesives, they like to have longer and shorter chains. And so one way they do that is they take the simplest, cheapest acrylate and just add a higher boiling alcohol. Methanol boils at like 54 and butyl alcohol boils at 101. So you just run the reaction and it goes to very high yields of the higher boiling ester. Okay, questions on that? So these hydrolysis and transesterification steps and esterification steps are all in equilibrium. So because of the reactivity and the basicity of the water and the alcohol, so you have to play some games to drive your equilibrium where you want it. Okay, so if we looked at the mechanism of that acid catalyzed hydrolysis of the ester, we're going to see the first thing that happens is we're going to get protonation of the carbonyl oxygen by the hydrogen. That's going to generate that more positive, partially positive carbonyl carbon here, and then we can have attack by our poor nucleophile, our neutral water species. Once we get attacked by that neutral water species, we have this intermediate here. And again, because the basicity of the alkoxide leaving or the hydroxide leaving is approximately the same, that in any one time, any one of these is going to leave. But as you add more and more water, it's going to displace more and more of the alcohol and give you more and more of the free carboxylic acid. So once you get to this step right here, all three of those oxygens are approximately equal in basicity. So any one of them can be protonated. And so then any one of them, and if one of the oxygens protonates, it goes back in this direction. If the alcohol protonates, we go to the forward reaction right here, where we can eliminate neutral alcohol and our lone pair will kick in here, generating our protonated carbonyl species. And of course, the deprotonation of our protonated carbonyl species will generate our carboxylic acid, our neutral alcohol, and regenerate our acid catalyst. Okay, so, and again, every single one of these steps is reversible. So to make it drive to your final product, if you remove this alcohol or if you add a lot of water, you can drive the reaction to the carboxylic acid as your primary product. Okay, so base catalyzed hydrolysis is a little different, okay? And I said it has to be promoted by because you're using an entire equivalent of it. So in the case of base hydrolysis, and it's typically called saponification, little history note, saponification is a process used by people for over 2,000 years, where they would take the sodium hydroxide generated from fire ash, and they would use it to clip off the esters in animal fats to generate soap. So that's where the soap word comes from. It's actually from the saponification of animal fats. It would generate a long chain carbon chain like a laurate and glycerin, which is the other part of natural fats. Anyway, so history lesson. Okay, so in the base catalyzed here, base mediated system here, we have a different mechanism because we don't have to protonate the carbonyl to make it more reactive because we have a strong nucleophile, okay? Our hydroxide here already has that negative charge. It's already a strong nucleophile, and therefore its first attack is going to generate our tetrahedral center here. And now we have a competition. We have a competition between hydroxide leaving as a base or the alkoxide leaving as the base. Okay, so, and again, it's reversible, so either one can leave. But if the hydroxide leaves, I'm sorry, if the alkoxide leaves first, we'll generate our carboxylic acid and our alkoxide salt, which can then deprotonate our carboxylic acid and generate our ester. I'm sorry, our alcohol here. Now, if you're doing this heated and your alcohol boils out of solution, you're driving the reaction to the deprotonated carboxylic acid. At the end of the reaction, you acidify your product there and you will generate your free carboxylic acid. Okay. So the reaction mechanism is very different from that because we're using a strong nucleophile. And once we remove this alcohol at the end, we no longer have a nucleophile to come in and attack that alkoxide, and therefore the reaction finishes. Okay. And again, I want to say the base is consumed in the reaction and is not regenerated. So you need at least one equivalent of base for each carboxylic acid you want to hydrolyze. All right, that is esters and all the different reactions we have with esters and what's driving those. Any questions on that before I move on to our last section, which is amides and nitriles? Okay, all right, so let's go. All right, so the last thing we want to talk about is our amides and nitriles. And of course, those are those carbonyl bonded to nitrogen or that carbon triple bonded to nitrogen. And so let's look at those and how we're going to play with those. And again, on the reactivity scale, the acid chlorides, then the anhydrides, esters, and then the amides are the least reactive of the set, okay? Which means we can actually make amides out of any of the other functional groups, okay? And in the case of the acid or the acid anhydride or the ester, we typically use the more basic amine base as our nucleophile, and it'll displace either OH or other things. And then we actually end up with our amide and we generate water as our final product, okay? Typically, it is done stepwise where it forms an acid-base salt first. And then by heating that acid-base salt, that rearranges and eliminates water and gives you your nitrogen carbonyl bond. Okay, so let's look at that mechanism a little bit more. No, we're not. Okay, another way to do it is to actually use a dehydrating agent. And what this does is this actually promotes the formation of the carboxylate to make it a better leaving group. Okay, so in the case of this, we were using, instead of heat to remove water, we're actually using a chemical reagent that will add water across it such that it can be removed as an organic compound. Okay. So in the case here, we use what we call dicyclohexocarbodiimide, or DCC. Okay. In the case of DCC, it looks something like this here. Okay. And the key feature here is that you have two carbon-nitrogen double bonds centered on this section here. The cyclohexyls here are just used to make it fairly soluble in many organic solvents. Okay, but all the magic happens right here in the middle, because what we're going to end up doing is we're going to add the oxygen of the water to the carbon in the center, and we're going to add the hydrogens of the water to the two nitrogens adjacent. And so what we're going to end up with is that weird thing with two nitrogens on it, a urea, and this material is water soluble and can be washed away. In the process, it generates our amide here. Okay. The mechanism is in the book, but don't worry about it. It's not that important. The important thing is that if you have a carboxylic acid and an amine, and you have a very expensive amine, so you only want to use one equivalent of it, if you use DCC, you do not have to have extra equivalents of that amine to get rid of any salts or other things that might happen. All right. Okay, so we can also make amides, of course, from acid chlorides, and we talked about that already, where we had attack by any primary, secondary, or ammonia, as long as it has one acidic hydrogen on it, it will generate our amide, okay? And one equivalent of HCl. So we typically use two equivalents of the amine. One forms a salt, one forms the amide right here, okay? And again, we do that same type of reaction with anhydrides. We're gonna end up forming one amide and one salt with the other half of the molecule, which is the carboxylate. And we talked about that a couple of slides ago. And of course, we can also displace the alcohol in an ester. Because the nitrogen is more nucleophilic than the oxygen of the alcohol, this displacement actually goes pretty well. It's not very fast, but it is pretty useful in the fact that we're not making a salt. We only need one equivalent of amine, and we'll regenerate the alcohol if we want. Okay. So now, if you have a cyclic anhydride, you're actually going to generate something that's a little different. And what that means is you're actually going to create what we call an amic acid. If you have an equivalent of an amine come in and react with a cyclic anhydride, instead of having the other half of the anhydride go off as the carboxylic acid salt, you'll end up with one amide right here, and then the other one is the carboxylate salt right here. Now, because we have the opportunity to form a 5-membered ring here, we can actually just mildly heat this, just a little over 150 degrees, and it'll actually cyclize that material, forming a new functional group we haven't talked about, which is a nitrogen with 2 carbonyls on it, and that's called an imide, I-M-I-D-E. But again, this is another group we'll talk about later, but it's made from the reaction between a primary or ammonia, a primary amine or ammonia, and will actually give us a dicarbonyl nitrogen compound that's a little different than the amides we've talked about before. Okay, so as I said before, we've moved down in reactivity. Amides are the least reactive of the carboxylic acid series, which means you cannot make an ester from an amide. You cannot make an acid chloride from an amide. The only thing you can make from an amide is hydrolyze it down to the carboxylic acid, okay? And so even though that our amines tend to be more basic than water or hydroxide, we can hydrolyze it down by adding excess amounts of water or hydroxide to drive the reaction to the carboxylic acid derivative. So in this case, we would do something like acidic water or water with hydroxide in it. Now, once you use this base-mediated system, again, you're generating a salt with the base, with your hydroxide here, so you have to use an entire equivalent to that. And then this doesn't react because now you've taken away its reactivity by having it as a salt. And then by acidifying at the end, after you remove your amine, you can generate your free carboxylic acid. Okay. In the case of acid-mediated here, you end up generating your amine salt plus your carboxylic acid as in its protonated form. Okay, so let's talk about the mechanism of the hydrolysis here. In the case of the base-mediated hydrolysis here, we're using the hydroxide as a nucleophile, and it's going to come in and give us our tetrahedral center here. Now, at this point, the hydroxide is not as good a base as the amine here. So we have to do something else to drive the reaction forward. So what we do is we actually remove a hydrogen from that hydroxide that just came on and generate a dianion with the oxygens here, okay? Because that proton on the oxygen is more acidic than the proton on the amine, okay? Once we've generated this dianion, now we have O2- as our leaving group. Those are very bad leaving groups. The amine now is the most favorable leaving group. It's the least basic leaving group. And therefore, when it gets protonated by water, it can leave, giving us our ammonium salt and our carboxylate salt here. Okay, so then after the end of the reaction, you can protonate to regenerate your protonated carboxylic acid. But see, so we're driving it forward by using it as a nucleophile and then deprotonating that hydroxide intermediate to make it a bad leaving group. Now the amine is still the least basic system, and it makes it the best leaving group. Okay, we're almost done. All right. So let's talk about nitriles. We talked about the cyanohydrin reaction in the previous system, and we talked about how that cyanide group is like a protected carboxylic acid. So we did these reactions in chapter 7 right here, our SN1 and SN2 type reactions using cyanide as a nucleophile. And so let's talk a little bit more about, that was what we can use these for. So one of the ways to generate nitriles in an organic, already attached to an organic system, is to actually start with your primary amide right here, and you have 2 protons here and 1 oxygen here. And if you dehydrate your amide, you're going to end up with a carbon triple bonded to a nitrogen, or our nitrile right here. So we typically have to use a very strong dehydrating agent. We can't just use heat. You have to actually use this oxygen grabber right here. And in the case of that, we use a thing called phosphorus pentaoxide, or P4O10. Or we can actually use strong anhydrides like this acetic anhydride. And what it'll do is it'll take the water away and generate our carbon nitrogen triple bond. And in the case of the P2O5, or the phosphorus pentaoxide, it'll generate phosphoric acid or acetic acid if we're using anhydride. Okay. So basically all we've done is dehydrate our nitrile to generate a new functional group. Okay, once we have that new functional group, it can be hydrolyzed either by acid or base. And so again, we don't need to know the exact mechanism there, but basically we're using acid to fully protonate our amine to make it a better leaving group, or fully deprotonate our oxygens to make our amine, again, the better leaving group. Okay, so one of the last things we're going to talk about with nitriles is using it instead of as a protected carboxylic acid, use it as a source of a primary amine. When we talked about substitution reactions in chapter 7 with the SN1, SN2, we said you had to use a lot of an alkyl halide, and you'd end up with a tertiary amine because the amine was so nucleophilic. So one way to stop at that primary amine is to generate your nitrile right here. And then by using lithium aluminum hydride, because that'll reduce down other carbonyl compounds as well, it'll actually reduce it down to the primary terminal amine. It's going to add 4 hydrogens across this triple bond, yielding our primary amine. Okay. So what's really good about this is that Dibol is also very good at transferring that hydrogen to the system, but instead of generating the primary amine, it's going to stop at that carbonyl compound. Remember, Dibol is one of those things we use to take an acid chloride down to an aldehyde. So it's going to do that same kind of selectivity, and our Dibol is going to take our nitrile down to our aldehyde and stop at that position. Okay, so we can generate from our nitriles either primary amines, aldehydes, or carboxylic acids if we go all the way to hydrolysis. Okay, so we can also use them as a equivalent to a carbonyl compound and do reactions like doing an addition across the carbon-nitrogen bond. So we can actually take our cyano compound here and react it with one equivalent of an organomagnesium or an organolithium right here. And then when we hydrolyze off the nitrogen species at the end, we'll actually generate ketones right here. So we can take a nitrile and make a primary amine. We can, with lithium aluminum hydride, we can make an aldehyde with our Dibol, and we can make a ketone with a Grignard reagent. So the nitrile group is actually one of those groups that we can do a lot of different things with. And again, it's one of those things that is kind of like a carboxylic acid, but kind of does some very different chemistry. Okay, so that is the end of chapter 17, part 6, and that summarizes all of 16 and 17 now. Okay. We have about 15 minutes. So the things I want to draw your attention to is, okay, both of these chapters deal with carbonyls, okay? And we can do lots of things with the carbonyls. We can do additions across them, think aldehydes and ketones, okay? We can make them by oxidation, think alcohols going to aldehydes and ketones, okay? We can make, if we oxidize our aldehydes and ketones too far, we get to the carboxylic acids, okay? So we can go aldehydes, ketones, carboxylic acids by our oxidation route. And we also have reducing agents. We can reduce carboxylic acid esters down to primary alcohols. We can reduce aldehydes and ketones down to alcohols as well. So we have opportunities to do addition reactions, oxidation reactions, and reduction reactions to go back and forth between all the different functional groups we have here in these two chapters. And that's the kind of common theme. That's why this is a great thing to have all in one week, because you get to see them going forward all the way to carboxylic acids and seeing them go all the way back to alcohols, all the way through just these two chapters. Okay. All right. I'll open it up to questions. We have a little bit of time here for questions, and then we can break for a little while and get on to our activity. I got the Zoom chat open. I've got my, I'm gonna pull up my blank slide here. Oh, that's not blank yet. All right, any questions on that? Again, if you're looking for a theme to study to, think functional group transformations and selectivity. How can I get just this functional group? How can I get from this functional group to that functional group? Sometimes it's like, well, okay, I can't get there directly, so I'm gonna oxidize it down to a carboxylic acid, convert it to an acid chloride, use dibol, take it back to the aldehyde. So, you know, it's looking at that forward and back is the key here. Okay, I'm gonna stop sharing and I'm going to stop recording.